2 filters, and 1572 of your rows answer to neither one. Latency over 200 milliseconds, 5,970. 200 or less, 32,458. Together, that's 38,428 out of 40,000 measured on this machine. The missing rows aren't lost. They're null, and a comparison with null is neither true nor false, so your filter refuses to answer. Today, filtering, sorting, and null. So ask Spark directly. Filter where latency is null and count 1572. Exactly the rows your 2 filters skipped, and every one of them is a request that timed out and never recorded a latency. The gap between your filters and your row count has a name, and you can query it. Episode 2.4 of the course. The next one builds straight on these nulls, so subscribe to catch it. Now watch what happens when you try to fix this the obvious way. Now the part that bites. Nobody deletes those rows and nothing breaks. They silently stop existing for your where clause. Watch. You'd expect not to rescue them, so run not latency greater than 200. 32,458 rows. The same fast rows, and not one timeout among them. Null greater than 200 isn't false, it's null. Not null is still null. And Spark keeps a row only when the filter says true. Every dashboard you build inherits that difference. Here is the rule underneath it, and it isn't a Spark quirk, it's SQL. A comparison returns 3 things, not 2. 1 greater than 2 is false, as you'd expect. Null greater than 2 is null. Null equals null is also null, and that's the one that catches people. 2 unknown values are not known to be equal. Only the null-safe equality operator returns true for that pair. 3-valued logic is the table your filters actually run against, and your data has nulls in it. So how do you ask for them? Not like this. User ID equals none compiles, runs, and returns 0 rows on any dataset forever. The one that works is isNull. 8,920 rows of anonymous traffic in this table. Its mirror is isNotNull for when you want them gone on purpose. And if you need an equality that treats 2 nulls as equal, the null-safe operator gives you 8,920 again. 3 ways to write it, one of them always wrong. Sorting has the same problem wearing a different face. Order by latency ascending, and the rows on top are nulls. Your timeouts arrive before the fastest request you actually served. Flip to descending and they move to the bottom, behind 456 milliseconds, the slowest real request in this table. So the top 10 slowest either opens with rows that have no value at all, or hides them, depending on one word. Spark gives you the explicit forms. Desk nulls last, ASC nulls first. Second ambush, and this one costs more. The obvious cleanup is na.drop. Run it on your 40,000 rows, and you get back 29,882. You just lost 10,118 rows, 25% of the table, and almost none of them were timeouts. Bare na.drop deletes a row when any column is null, and most of yours were only anonymous users. Pass a subset and you keep them, 38,428. Let's reproduce the scoreboard. Read the logs with a declared schema, then count twice. Count star gives 40,000. Count of latency gives 38,428. Same table, same column. Average latency comes back 122 milliseconds, and it is the average of 38,428 rows, not 40,000. Aggregation skip nulls without telling you. Fill the timeouts with 0 instead, and the average drops while your data quietly lies. Every frame here is that script's output. So here's the rule. A comparison with null is neither true nor false, so every filter you write on a nullable column is a decision, whether you make it or not. Make it. Add isNull or isNotNull when the column can be null, and say what you mean. Drop with a subset, never bare. Fill only when 0 is honest for that column, which for a timeout it never is. And when 2 counts disagree, count your nulls before you hunt for a bug. Next episode, group by and aggregations, where that same null changes every average you compute, and a shuffle decides the speed.